in last few lectures, we have talked about solution of one-dimensional transient diffusion equation using explicit scheme. We have also seen that explicit scheme has certain issues. The scheme seems to be unstable for some reason that we don't know yet. So here in this lecture, we will see that what is that criteria that makes explicit scheme unstable, and then how do we stabilize explicit scheme. So let us once again recall that we are considering the one-dimensional transient diffusion equation, that is partial derivative of u with respect to time is equal to alpha, the diffusivity, multiplied by this double derivative of u with respect to distance x. Numerically, when we try to solve it using explicit method, the difference equation turns out to be like this. We have ui as n plus 1th time step equals ui at nth time step plus certain correction. That correction is r multiplied by ui minus 1 minus twice ui plus ui plus 1 at nth time step. This r is alpha delta t divided by delta x square. Now if we solve this equation, this difference equation, in an infinite precision machine, we have a solution d, and if we solve it in a finite precision machine, we have a solution n. The difference between them is our round of error. So an infinite precision machine is an hypothetical machine that has the capacity to represent a real number with infinite precision. It will not truncate any real number. But that cannot happen in reality. In reality, when we are using real numbers such as root over 2, we have to truncate at some point. Otherwise, it will simply go on infinite times. So our hypothetical infinite precision machine can take care of these infinite numbers. But a practical computer or a calculator cannot. So a practical machine is finite precision, and it gives us a solution n, which basically means that this round of error we cannot avoid, since all practical machines will have limited memory, and therefore there will be always some sort of finite precision in our machine, no matter how good it is. Now that I have this error epsilon, my round of error always, how this error grows, that is the question that we are going to ask here in our discussion of stability. Both this n and d, they are coming from this difference equation. If I solve this difference equation in infinite precision machine, I get this d. If I solve it in finite precision machine, I get this n. But both are following the same difference equation. So the difference between these two equations, that will give us an equation of round of error. If I subtract these two equations, n minus d is my round of error. So it gives us an equation that epsilon I at n plus 1th time step is equal to epsilon I at nth time step plus this r multiplied by epsilon I minus 1 minus 2 epsilon I plus epsilon I plus 1 at nth time step. The point that we are really concerned about, that as I go from n to n plus 1th time step, what happens to this epsilon I? It will increase, it will decrease, or it will remain same. That is what we are concerned about. And especially we want to avoid a situation where this epsilon I n plus 1 will actually grow as compared to epsilon I n. We hope that our solution scheme is such that this epsilon I n plus 1 will be less than epsilon I n. Then the scheme will be stable. Therefore, to define this stability, we bring this new idea of growth factor or amplification factor. This is defined as epsilon I n plus 1 divided by epsilon I n, which means I divide both sides here by epsilon I n, and it gives me 1 plus r multiplied by this 2 becomes 2 because I am divided by epsilon I n. But other two, we have some ratio, epsilon I minus 1i and I plus 1i, this ratio. So we are concerned about this particular factor g, and we hope that this g will be less than 1 in its absolute value. It will be plus or minus, that is not our concern. In fact, these errors are random, so randomly it could be pluses or minuses, that we really don't care about it. But all we want is that the absolute value of g should be less than or at best equal to 1. If it is equal to, then we will say that error is there, whatever it was there before, but at least it is not increasing. Ideally, it should be less than 1. Then we will know, find my error, that is round of error, is actually decreasing. So now let us see that to know that it will be less than 1 or greater than 1, now we need to know some idea about this epsilon. So what kind of expression can we derive for epsilon? You see, this sort of difference equation, it indicates that epsilon, of course this is not really continuous, but it is somewhat, if it is continuous, it will obey this kind of an equation, because when we discretize this kind of an equation, we get this kind of difference equation. So that gives us some idea that what kind of solution epsilon might take, because we have solved such equation analytically already. From analytical solution, we know that the nature of solution of this equation will be using separation of variable. If we use, that would be a product of two functions, epsilon 1t and epsilon 2x. This is a homogeneous linear equation, and boundary condition could be homogeneous, and I am coming to this point. With homogeneous boundary condition, we can have this kind of a solution. And if we have this kind of a solution, if we propose this kind of a solution, as we have already done in separation of variable approach for the analytical solution of one-dimensional transient diffusion equation, then we can actually break this as first the time derivative. If we take, that will give us the time derivative of epsilon 1. Epsilon 2 will remain unaffected because it is a function of x and not a function of time. Similarly, the spatial derivative will give the spatial derivative of epsilon 2. It doesn't do anything for epsilon 1 because epsilon 1 is only a function of time. Now we can plug this in the main equation, and what we get is this epsilon 1 prime divided by epsilon 1 is equal to epsilon 2 prime divided by epsilon 2. Since this is a function of t and this is a function of x, their equality gives us the idea that they should be equal to a constant. And as we have seen before, that this constant has to be a negative. If it is not a negative, then it will simply grow in time, and then it is of no use for us. So let us see with this idea, what can we get? We have epsilon 1 is a exponential minus lambda squared t, and this epsilon 2 is, we can write it in sine and cos. We can also write it in exponential with this imaginary j, where I am keeping this j as root over -1. Usually we write that as I, but since we are using I for other purpose, I am writing it as j. So you write it this way or you write it in sine cos, it doesn't make a difference. But this complex number will help us to manipulate here. That is why I am keeping it complex. Now we have to apply homogeneous boundary condition. Now, why homogeneous boundary condition? So consider this case that I am solving between x equals 0 and x equals L. I am solving for my unknown temperature or u or any other variable. I am solving this diffusion equation ut is alpha u xx, and I am having this kind of random error coming over here. So that random error could be anything. It could be anything, anywhere. We don't have much control over it, which basically tells us that at some point it will cross 0. Somewhere it will be 0, somewhere it will be positive, somewhere it will be negative. So wherever it is 0, we pick those kind of points, 0 points, and between these two 0 points, if we solve it, then we have homogeneous boundary condition. With this homogeneous boundary condition, you know from our discussion of analytical solution of heat conduction that this solution will come as a series of this sine and cos term. Some of them will go down to 0, etc. will happen. But anyway, it will be series like this. Here I am not writing sine and cos. I am simply writing exponential this j, which is root over -1 kmx. There will be m terms here. Actually, there will be infinite terms here. M will go to infinity. So m is a parameter that is giving us the series here. There is this am exponential certain constant beta m t exponential j kmx. This km could be positive or negative. If it is negative, it will give us this minus j type expression, and there will be infinite number of terms like this. Now, we cannot really do much about infinite number of terms, but if you look at it, this exponential j's, they are actually sine cos. So they are actually wave in nature, and this exponential of time t, that indicates the growth or decay of that wave. So for each m, I have one of this term. So essentially what do I have is that for each m, I have an independent wave that is either grows or decays in time depending on this bmt. It will grow or decay in time. So each wave, they are summed up together to give me this round of error, and I cannot really follow each wave. So what I'll do, I'll take one wave and see what happens there, or in other sense we call this taking up one mode. So the growth of one wave we'll see, and from that you will see that we will gain sufficient insight to comment on the stability of the problem. So let us say this is my one of this wave, this am bm tn exponential j km xi, and this is at location I at time level n. This is a summation of series, of course, but I am taking only one such wave, one term from that series. So if this is my epsilon I n, then this only one mode that I am considering, from this I can find the mode adjacent to it, and from there we'll be able to establish an expression of g, that is the growth factor. So let's see how we'll do so. First is, if this is at I, then I plus minus 1, if I go one step on right side or left side, I is my spatial index. So here, this is where only I have I. So my xi, I'll go either plus 1 or minus 1. Now, this xi plus 1 and xi, the difference between them is delta x, and we see that the ratio of epsilon I plus minus 1 divided by epsilon I n will be exponential jk xi plus minus 1 exponential jk xi, because these terms will cancel out. Well, here, as it comes out to be xi plus minus 1 minus xi, I'll get either plus of delta x or minus of delta x using an uniform grid. Because xi plus 1 minus xi is delta x, and xi minus xi minus 1 is delta x. Therefore, I'll get this is plus or minus of delta x. Now we go back to the definition of g. We have defined g in this way. So g is 1 plus r. R is alpha delta t by delta x square. That is epsilon I minus 1 divided by epsilon I minus 2 epsilon I plus 1 by epsilon I all at nth time level. Now I already have the expression for these terms. I'll simply plug them in. So let us do so. So it gives us the first term I minus 1 by epsilon I. It is coming from here. It will give us minus of jk delta x. And the second term, this I plus 1 by I, it will give us plus jk delta x. Well, so this e to the power minus ix, e to the power plus ix, sum of them should be equal to twice of cos x. So I am taking this km delta x as beta for simplicity. Then I have this e to the power I beta plus e to the power minus I beta divided by 2 is equal to cos beta. So I bring it up here. It looks very slim expression now, but still we don't know beta, therefore we don't know g. Now the point is that this is only one mode we are talking about, the mth mode. And mth mode will give us some value of km, and that will give us some value of beta, which we don't know. But what we can do is actually we can see what is the worst possible mode, which beta will give us the highest value of k. That will be the worst possible mode, and that is where we can calculate g, because the idea is that if there is a possibility of having a worst mode, in reality that worst mode will probably happen. So we calculate for the worst kind of mode. We write this as 1 minus 2r, 1 minus cos of beta, and 1 minus cos of beta we can write it as 2 sine square beta by 2, the usual trigonometric identity. Now our goal is to see that for worst case scenario, I want to keep my g in an absolute value less than 1. This is my condition. So what will be the worst case scenario? What would be the value of beta that will give me maximum g? That's what I'm going to see. So it means that this g value, whatever I have, for stability, I have to keep it confined between 1 and negative 1. Now 1 minus, so let us take this, there are two conditions here. One is this minus 1 less than equal to this g, and another is this g less than equal to 1. So we have to investigate both of them. If I take this condition first, then 1 minus 4r sine square beta by 2 less than 1. What does that tell us? It tells us that I can switch the sides. So it tells us 4r sine square beta by 2 should be greater than 0. Well, so this term should be greater than 0 actually, or at best it should be equal to 0, because this term is sine square. So sine square should be within 0 and 1, and this r is alpha delta t by delta x square. So it would be a positive number. So this is a positive number, and sine square is between 0 and 1. Therefore, this 4r sine square beta by should be greater than or equal to 0. Therefore, this condition is satisfied anyway. So we have to focus on the other side, that is minus 1 is less than equal to this g. So from this condition, what we get is 4r sine square beta by 2 should be less than or equal to 2. Or in other sense, r should be less than or equal to 2 by 4 sine square beta by 2. Or this r should be less than 2 by 4 sine square beta by 2, the minimum value of this. If r is less than the minimum value of this, I don't know sine square beta by 2. So what I have to do is that I have to see that for what kind of situation this value will get its minimum. If r is less than that minimum, then r will be always less than this particular function of beta, that is 2 by 4 sine square beta by 2. And then if r is less than this, my scheme will be stable. So what makes this term minimum? Okay, when sine square beta by 2 will attain its maximum, then this 2 by 4 sine square beta by 2 will get its minimum. And I want to keep r less than the minimum. So what is the minimum of sine square beta by 2? What is the maximum of sine square beta by 2? Well, that should be 1. It cannot go any further because this is sine function, which tells us r should be less than or at best equal to 1 by 2. Under this condition, this g should be less than 1 and we have a stable scheme. And we know that r is alpha delta t by delta x square, which tells us that the stability condition for explicit scheme is this alpha delta t divided by delta x square should be kept less than 1 by 2. Therefore, if you just blindly reduce delta x, when we are simulating, we blindly reduce this delta x hoping that if my grid is small, I'll get a better solution. You will not. Because smaller delta x means this alpha delta t by delta x square, this will increase. And if it increases above this 1 by 2, then my solution will become unstable and you will get unphysical oscillations, unbounded result. If we reduce delta x, we have to reduce delta t also, such that this ratio always remains less than 1 by 2. This is the condition of stability for explicit scheme. Now, this g, we know that expression of g, that is 1 minus 4r sine square beta by 2. If I plot that expression here, we find that with beta is basically an angle, so it can go from as such 2 pi on positive side, negative side. After that it will simply repeat itself. So this is 2 pi here, and I plot it for various r because r is something that I might vary in different programs, different runs. If I plot it, you see that r equal to 0 is a limiting case. It has no practical value. But what happens is that here, as I increase the value of r, it is coming first toward 0, and that is a good thing. Around this point, around r equals 0.25, it is coming on negative side, and on negative side it is hitting 1 at r equals 0.5, so this is just marginally stable. Beyond that, you can see that this is negative 1.5, that means g has gone beyond 1. So these are the parts where things will be very likely to be unstable. Therefore, this explicit scheme is conditionally stable. It could be stable for r less than 1 by 2, but it may be unstable for r greater than 1 by 2. So whenever we are changing this delta x, we have to be careful about delta t, and if we reduce delta x, we have to reduce delta t accordingly. Thus, for explicit scheme, the time step is restricted. Time step we have to always check, and we have to keep it small to keep the scheme stable. This kind of technique is known as von Neumann technique or Fourier stability analysis, although this kind of approach was first shown by Nicholson, who is working to improve the explicit method, and she understood the problem of explicit method and she derived a new method, which is Crank-Nicholson method. We will come to that later. That is a very, very efficient method as compared to the explicit. Von Neumann analysis, of course, you have already seen that it follows only one mode. So this is a sort of modal analysis. But the main point is that error may be the summation of many such modes. But if we follow one mode, and if we follow the worst mode, then we'll get an idea that how this error will behave. Of course, following one mode and for our analysis, this is possible only when things are linear, because linearity gives this superposition. You can break the modes and you can take one mode and analyze it. For nonlinear PDE, that is much more difficult, and that is of course beyond the scope of this course, but just to give you an idea that there is no such good theory just like this for stability in nonlinear PDE. So that is still an open question in numerical solution of partial differential equations. So now we are going to summarize. The stable algorithms, as you have seen, it will suppress errors, but unstable algorithm will enhance them. Here, of course, error means random errors coming from rounding off of real numbers. Systemic errors such as human errors. I may have made a mistake while writing the program. This kind of errors we are not considering. That kind of errors, we have to take care of that through proper validation, verification. Once we are convinced that we are not making any mistake, then only we can talk about this question of stability or question of random errors. For your exercise, you go back to that explicit solver that you have already seen and verify that the solver is always stable for r less than 1 by 2. You run that for many different delta t and delta x's, but keep the r less than 1 by 2 and verify that it is indeed always giving you a stable solution. Not necessarily the solution will be always good. Solution will be always highly accurate. But what we are claiming that when r is less than equal to 1 by 2, solution will be stable. That means it will not show this unphysical undulation and unbounded errors. So that's all for this lecture. Thank you, and I'll see you in next class.